I want to thank Brian for the invitation. And following the two wonderful talks on magnetars, we changed the flavor, talking about the interacting neutron stars. Vicky already reviewed this, just very briefly go through the observation properties because I need them. So short duration, high glide, high rate, these everybody knows. High redshift, there's a nice relation actually, roughly this number. I'm happy to see that the data actually fit this one well. High brightness temperature, typical frequency in this range, spectral index, frequency downdrifting, we all heard this from Vicky. Polarization properties, so it's very diverse, mixed, 100% linear polarization in some, but low polarization in some others. Some have circular polarization, constant polarization angle in each burst, in some bursts, but varying polarization angle in some others. We already heard, and I'll show another case for a repeater. Large RM for this guy, but regular or low RM for all the others. And there's a secular and short-term variation of RM. Repetition, so there's a whole lot of discussion by Vicky and Laura, but I want to emphasize these 2 points. So one is this repetition could be quite frequent during the very recent observation campaign with FAST, the 500-meter telescope. Within 40 days, they detected more than 1,000 bursts. So to me, we need very inexpensive way to make bursts, like efficiency of like 10 to minus 6, you need a lot of energy, a lot of triggering mechanism to do that. But something relatively inexpensive ways doing repeating FRBs probably, to me, is preferred. And there's no evidence of decreasing rate with time. As I just said, recently there's another 1,000 bursts from this guy. Looks like after almost a decade, there's no evidence of slowing down. All right, so we back to this question, nature or nurture. The magnetar, of course, belong to the nature part, so everything comes from the star itself. I'm going to talk about the other category called nurture. So in interacting neutron stars, we need something else. So the possible energy powers, as Ben already reviewed, there's an intrinsic power, which is spin down, and a magnetic power, but there could be extrinsic powers, which is kinetic power and gravitational power, which I'm going to use to produce repeating FRBs. Okay, so with all due respect to Brian, Ido, Ben, who wrote this very influential paper to begin with, because it's a very popular model. So I believe everybody in this room, myself included, theorists and observers, we are all riding this bandwagon. But I want to be more critical a little bit, because we should ask ourselves after this many years, is it a fact or wishful imagination? So you guys, I already expect these things, but let's just go down to the list a little bit. So Brian was saying, okay, so the very first, I think we are all misled by this first guy. So it's not your fault, not everyone. It's just this very first repeater is so special. So so it has a host of long GRBs and supernova. Then we expect, okay, so all the FRBs should have this. But the answer is no. Most are not in old environment, in star-forming galaxies, but they are not like very active star formation, or sometimes you are in elliptical galaxies. Of course, we can start to turn around saying, okay, maybe still magnetars, but not produced from supernova explosion, but from neutron star mergers. So we produce a long-lived magnetar that way, of course. And then one should detect FRBs from long GRBs and superluminous supernova remnants. This is a very good test. If we see one of them, would be excellent. But so far, there's a lot of searches following GRBs, following supernova. We see some. We haven't seen any FRB yet. Of course, we see some persistent radio sources. We are very happy about it, but we should not be too happy about it, because from a magnetar can produce a remnant, but it does not necessarily mean that those magnetars can make FRBs. So we really hope to see in the future indeed one FRB is detected following one of these explosions. That will be a great proof to us. And FRBs should have large RNs because the magnetar tends to have magnetized wind, except for this guy, others are not. So of course we can say that this guy is a repeater. Repeaters should have large RMs, and now repeaters, we hope to do that, but except this one, others are not. Then we can say this guy is very young magnetar because he's very active. The others are not active enough yet, but this guy I'm going to talk about is also very, very active, comparable to this guy, but RM is still small. So none of the predictions, this is a little bit harsh, but this might have been fulfilled so far. I hope really one day one of these predictions will be fulfilled. That is great proof. So why shouldn't we seriously consider other possibilities? So that's actually, that's why I want to give this talk. Other issues, these issues are actually solvable. I'm just listing as a more critical part. So can an engine trigger burst so frequently, relentlessly, so continue doing it? So you really need to have something triggering that all the time, and no evidence of declining activities. So we heard that the magnetars have a single Zhang Basar model, have the magnetosphere models. A single Zhang Basar model of frequency is low, 10 to minus 4 actually is, we just heard is 10 to minus 5 or even 10 to minus 6. So that needs a lot of energy. And for magnetosphere origins, we haven't detected any spin period. Of course, we can talk about all possibilities to remove that. I'm not saying these are, there are evidence against them, just these are issues. Polarization angle swing. So I will show that this actually, to me, this favors this model. But for those polarization swing cases, if we really play with the simple rotating vector model, which is valid for radio pulsars, it does not work. Okay, so we don't know what FRBs are, but we know these two neighbors, GRBs and radio pulsars. People trying to theorists like us, we're trying to borrow our wisdom from the other two fields to understand the FRBs. Lessons from GRBs, so we just heard from Ben and from Andre, relativity outflow, internal, external shocks. But there are some older ideas about possible coherent radio emission from GRBs, but so far we haven't seen any coherent radio emission associated with any GRB. In any case, those ideas have been borrowed in the sense of single Zhang Basars. There are so many papers and talks discussing this. And lessons from the radio pulsars. Radio pulsars are the real ones that produce coherent radio emission that we know for a long time. So there are internal inside the polar cap, near the light cylinder, even outside light cylinder, current sheet, those places. For the normal pulsars, we have this radius to frequency mapping. Somehow it comes from the inner magnetosphere. And there could be a third possibility. We know this double pulsar. The second one is actually somehow modulated, probably very likely have such kind of configuration. The strong wind from the primary actually shaping the radiation beam of the secondary. So that is something I want to borrow. So lessons from the pulsars, we do know that pulsars can make high brightness temperature coherent radiation. The emission is made bottom up, not top down, all related to magnetospheres. Okay, so I want to make the argument that very likely radio emission is related to magnetosphere emission. So this downdrifting, this feature, we heard about the interpretation within the Basar scenario, but within the magnetosphere, as long as you have open field line, just use curvature radiation, then you naturally have this frequency going down. Of course, the Lorentz factor cannot evolve too much. This might be related to the radiation reaction limited regime. So either from the inner magnetosphere or in the cone model from the outer part. As long as it's coherent open field line, you can do this. Okay, so these are smoking gun to me, so no Twitter, please. The paper is still being reviewed. So this is the fast repeater. It was actually originally detected with Parkes, but later you can see a variety of polarization angle swing. So it's not constant. And the evolution is very, very weird. So you cannot really fit within the simple rotation vector model. And very interestingly, RM in these different bursts is actually also evolving within a short period of time. So this is a pulsar. Using the same technique, pulsar RM is not evolving, but for FRB, you can see it goes up and down. So it's almost 10 sigma confidence level variation RM. Sorry? Fast. Yeah. So this model, this was my old model I was talking about cosmic cone back then. But the idea is instead of using the internal power, we have external kinetic energy, either from AGN, GRB, supernova, TDE, or binary companion, as long as something is hitting the magnetosphere, the foreground neutron star will change the configuration and suddenly release some radio waves. So within this picture, actually, it's quite flexible, but it works well. So you can interpret essentially every case. In this case, it's a special case in the sense that it is near an AGN. So it is the supermassive black hole is really pumping kinetic flow to the foreground neutron star and to make these repeating bursts. And then in Ricky's repeating periodic FRBs, and we have a companion, we have a binary system. So Kunihito Ioka and I is working on a paper on this. We actually test the different parameters, either for massive star plus neutron star or binary neutron star systems. We can find the parameter regime to produce this. Of course, the orbits need to be centric. Okay, so finally, I don't have much time. I'll talk about another possibility. This is interacting binary neutron star. So this paper was just accepted to FG Letters, and I posted to archive, but it won't show up until tonight. So please go there and take a look. So the bottom line is, so we all heard about binary neutron star mergers, but I want to add this magnetosphere. So of course, we have a lot of models showing that right before the merger, there's a one-off FRB. But according to my estimate, actually decades to centuries before the merger, the two magnetospheres already starts to interact with each other. So there's a lot of interesting things will happen. Reconnection, sharing, you can transfer some energy from the orbital energy to the energy to the stars. So basically, so we have the observationally, we have FRB energy of that order. So we have rotation. So this, I'm taking the double pulsar as an example. So we have rotation energy from A and B. We have a huge orbital energy. So we can really have enough energy just to power these repeating FRBs. And the orbital period in this scenario is about 100 seconds. So within this scenario, we should look at the characteristic period at tens of milliseconds for pulsar A, several seconds for pulsar B, and 100 seconds for the orbital period. So those are the three characteristic timescales. Of course, the fourth characteristic timescale is a lifetime for this because it takes, in this particular scenario, it's 500 years. But if you change the parameters, it varies from decades to centuries. So this FRB source can live for decades to centuries. And then interestingly, so these are model features, relatively inexpensive. You have large energy source available, and you have diverse polarization angles because we are talking about the reconnection of two dynamically interacting neutron stars. We don't really expect it's just a simple rotation vector model. And the short-term RM variation is possible because the dynamically evolving the magneto environment. And the hosts should be similar to short GRBs because these are decades to centuries before the mergers. So some of this off-center FRBs should be accounted for. Predictions. So I just mentioned the 3 time scales. We can look for those. Lifetime is decades to centuries. So these two are very interesting. So for magnetars, we expect that the activity will decline with time because it is spinning down, magnetic energy is depleting. But for this model, we got the 2 neutrons that get closer and closer and closer. You have more and more energy. So the activity should elevate with time. That is one prediction. The other is if you, because for 100 seconds orbit, the gravitational wave frequency is in the band of the LISA. So once LISA is up there, we can just look at some very nearby repeating FRB sources. And if they're close enough, they should be detectable. So that's another prediction. Okay, so this is my summary. The young magnetar, I talk about the nature. We still need to test it, but for interacting models, we have these possible supports. So thank you.